In this video, we're going to present the solutions to the tutorial problems for topic 6, what makes a car stop. Problem 1. In this problem, we're told that a 20-kilogram child stands on a set of scales in the lift. So the mass is equal to 20.0 kilograms. Calculate the mass reading on the scales when A, the lift is travelling downwards and accelerating downwards at 2 meters per second. So in this case, we've got a downwards velocity, but more importantly, we've got a downwards acceleration. So here's the child standing on the set of scales. The forces acting on the child are, we've got the normal reaction force from the scales on the child, and we've got the weight of the child going downwards, and then the resultant force is ma downwards. And so according to Newton's first law, we can write that the resultant force, which is the mass times the acceleration, which is downwards, is equal to the sum of the forces acting on the child. So this is the normal force upwards plus the weight force going downwards. Now the reading on the actual scales will be determined by this normal force. So what we need to do now is find the normal force. So the normal force upwards is equal to the mass times acceleration downwards minus the mg, which is going downwards. So what we can do now is we can take the mass out as a common factor. Now we've got minus g downwards, so that's 9.8 upwards. And then we've got plus a downwards. So if we take downwards as negative, then that's minus 2.0. We're given the a in the question. And so this is equal to 20.0 times 7.8, which is equal to 156. And now in order to get the reading on the scales, rather than reading off as a force, the scales actually read off as just a mass. So we have to divide this by g, or 9.8. So this is 156 divided by 9.8, which gives us 15.9 kilograms on the scales. Okay, part B. We now have that the lift is travelling downwards but slowing down. And so as the lift slows down in the downwards direction, the acceleration is actually in the upwards direction. And we're told that the acceleration is equal to 3.0 meters per second per second. So what we're going to need to do is do the same thing as we did up here, use Newton's second law. So we've got the mass times the acceleration, but the acceleration is in the upwards direction this time. And we've still got the normal force and the weight force acting on the child. So we've got the normal force acting upwards, and we've got the weight force acting downwards. And so the normal force upwards is equal to, in this case, the mass times the acceleration, which is upwards, minus mg downwards. And so this is equal to m. Now the acceleration in the upwards direction is 3.0 meters per second, and we've now got minus 9.8. So this is equal to plus 9.8 meters per second. And so this is equal to 20 times 3 plus 9.8 gives us 12.8. And solving this on the calculator, we get 256 newtons. And then we want to convert it to a reading on the scales. So in order to convert it to a reading on the scales, we divide by 9.8. So we've got reading on scales is equal to 256 divided by 9.8, which is equal to 26.1 kilograms. Now part C. In part C, we're told that the lift is now travelling upwards, and it's accelerating upwards with a rate of 2.50 meters per second. And so once again, we just do the same thing. We've got Newton's second law. The mass times the acceleration, which is upwards, is equal to the normal force, which is upwards, plus mg, which is downwards. And so we've got the normal force is equal to the mass times the acceleration upwards minus g going downwards. And so the acceleration upwards, we've got 20.0 times 2.50 and then minus 9.8, so that's plus 9.8. And so solving this on the calculator, we end up with 246 newtons, and so the reading is equal to 246 over 9.8, which gives us 25.1 newtons. And finally, part D. In this case, it's traveling upwards but slowing down, so it's decelerating, and so the acceleration is in the negative direction and is equal to 1.0 meters per second per second. And so we just do the same thing. Mass times the acceleration, but the acceleration is downwards, is equal to the normal force upwards plus the mg, which is going downwards. And so the normal force is equal to the mass times the acceleration downwards minus g downwards. And so this is equal to 20.0. Now the acceleration downwards, to account for the downwards, which is negative, we have negative 1.0 minus g downwards. G is minus 9.8, so this is plus 9.8. So we've got 20 times 8.8, and solving that on the calculator, we get 176, and so the reading is equal to 176 over 9.8, which gives us 18.0 kilograms. And so that's how we answer that problem. Problem 2. The tallest building in the world is the Burj Khalifa in Dubai. It stands 830 meters tall. So you get in the lift and travel to the top, and the lift accelerates upwards at 3 meters per second for the first half of the journey, and then it decelerates at the same rate for the second half of the journey. So let's draw a diagram. Here's the building. It's 830 meters tall. So halfway up is 415 meters. So you have an acceleration of 3.0 meters per second for this part, and then an acceleration of minus 3.0 meters per second for this part. So this is an acceleration downwards because you're slowing down. And part A says, what is the maximum speed of the lift during the journey? So to work this out, the maximum speed actually needs to be here, because up to this point we are accelerating, getting faster and faster, but after this point we start to decelerate, and so we'll be getting slower and slower. So the fastest will be is at 415 meters. So we need to find speed at 415 meters. So we'll need to go back to the kinematic equations in order to do this. And we know that we start from rest. When we get into the lift isn't moving, so the initial velocity is equal to 0. And so we can use the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance, which in this case is the height. Okay, so we've got v0 squared, that's 0 squared, plus 2. Now the acceleration is 3.0, and the distance which we cover is half the height, so 415 meters. And so this gives us that v squared is equal to 2,490, and so taking the square root of this, we get that the velocity halfway up is 49.9 meters per second. And then part B. So we should give this answer to two significant figures. So this is 50 meters per second to two significant figures. Now part B says, how long does it take the lift to get to the top of the tower? Now this is going to be absolutely symmetric because we're speeding up and slowing down at the same rate. let's work out how long it takes us to get to this halfway point. So to this halfway point, we can use the kinematic equation. V is equal to V naught plus AT. So V, we know that when we're halfway up, our speed is 49.9 meters per second. The initial speed down here was 0 meters per second. The acceleration is 3, and the time, that's what we're trying to find. So T is equal to 49.9 on 3. And solving that, we get 16.6 seconds, which is equal to 17 seconds to two significant figures. But that's the time to halfway. Now at halfway, we're travelling at 49.9 meters per second upwards, but at the top, when we get out of the lift, we've stopped, so we're at 0 again, but we have this acceleration here. So to work out the time, we can use V, the final velocity is 0, is equal to 49.9 minus 3t, and this turns out to be the same as this. T is equal to 49.9 on 3, and so this is equal to 16.6 seconds, and so the t total is just equal to 2 times 16.6 seconds, which is equal to 33 seconds to two significant figures. So you can see that that's symmetrical. The time to get to halfway up was the same as the time to get from halfway up to the top of the building. Now part C says, what is the maximum normal reaction force felt by a passenger with a mass of 90 kilograms in the lift? Okay, so let's try and do that in this space here. Here's the passenger standing in the lift. Now in this first half, the resultant force is equal to ma upwards. The forces acting on the passenger, we've got the weight force downwards and the normal force upwards. So we've got that because of Newton's second law, ma upwards is equal to the normal force upwards plus mg, which is going downwards. And so the normal force upwards is equal to ma upwards minus mg, which is going downwards, and so this is equal to 90 times, now this is upwards and it is 3, and then we've got minus 9.8 downwards, so that's plus 9.8. Now in the second half, this lift is going to be slowing down, so instead of being a plus 3, this would be a negative 3, and the reaction force would be smaller. So the maximum reaction force is going to be in the first half when the lift is accelerating. So that makes sense. When you're standing in a lift, when it starts to accelerate up, you feel a lot heavier, and that's because of the reaction force. So let's calculate what this is now. When we put this in the calculator, we get 1,152 newtons, and then we should just give this to two significant figures, so that's 1,200 newtons. Is problem 3. In this problem, we've got a block placed on a slope. The block has a mass of 5 kilograms. The angle of the slope is 30 degrees. The length of the slope is 2 meters. And we're told that the coefficient of kinetic friction is equal to 0.30. Now in part A of this question, we're asked to draw a diagram showing all the forces acting on the block. So let's do that now. Let's draw the forces in green. So first of all, we've got the weight force. So the weight force for the block acts directly downwards. We've then got the normal force of the slope pressing up on the block. So this acts in a direction perpendicular to that slope. So that's the normal force. And then finally, we've got the friction, which is opposing the movement of the block down the slope. So the friction is in that direction. So those are the three forces acting on the block. As a result of those forces acting on the block, there is a resultant force, which is ma, down the slope this way, making the block accelerate down the slope. So this isn't really a force which is acting on the block, it is the result of these other three forces which are actually acting on the block. So part B says calculate the normal reaction force of the block on the slope. So we need to calculate this force N here, which is perpendicular to the slope. Now, in order to do that, we can make use of Newton's first law that says that an object in rest will remain in rest unless acted upon by an external force. In the direction perpendicular to this slope, the block is not accelerating. So what we can do is split these into parallel and perpendicular to the slope components. And we then know that the perpendicular components must all cancel each other out. So this weight force can be split into a component which is parallel to the slope. So this is parallel to slope. It's directed directly down here like this, and then another component which is perpendicular to the slope. So this is parallel, this is perpendicular, so there's 90 degrees between these ones. So that's a right angle triangle there. Now to work out what the angles are, as this one's parallel to the slope, that angle in there is 30 degrees, as this angle here is 30 degrees. So this angle up here is 60 degrees, and if that's 90 degrees and this is 60 degrees, because all the angles in a triangle add to 180, we know that this one must be 30 degrees. And so this side is equal to mg sine 30. That's just from SOHCAHTOA. We know that sine is equal to opposite, which is this side, over the hypotenuse, which is the mg. So the opposite side is just equal to mg sine 30. And then using the car part, we have cos 30 is equal to this side. Let's just give it a symbol, let's say x, over mg. And so this side, the perpendicular side, is mg cos 30. And now we've said that perpendicular to the slope, all the forces have to be balanced. And so this normal reaction force must be equal to the weight force acting perpendicular to the slope. So we have N is equal to mg cos 30, and it's in the direction shown. Now we can actually come up with a number for this because we've got 5 kilograms times 9.8 times cos 30. Solving that on the calculator, we end up with 42 newtons, and that's to 2 significant figures, just because the mass is given to 2 significant figures. So that's part B. Now part C says calculate the frictional force experienced by the block as it slides down the slope. Now that we've calculated the normal reaction force, this isn't too hard. The force due to the friction is equal to mu k times the normal force. And so this is just 0.30 times the 42. We'll keep the significant figures here. I didn't write them all down, but let's put this as 42.4, and then we'll give our final answer to 2 significant figures again. And this gives us 12.7, which is 13 newtons. And this is directed up the slope, and is to 2 significant figures. And then part D says calculate the net force on the block. So this is this MA downwards. Now what we know is that the perpendicular components completely cancel each other out, so we can ignore those, and it's only these parallel components that matter. So what we've got is the component of the mg force down the slope and the friction force up the slope, and they act in opposite directions. So we've got the F total is equal to the weight force down the slope, which is the mg sine theta. So mg sine theta minus the frictional force, because they're acting in opposite directions. So we've got this negative sign here. So this is equal to 5.0 times 9.8 times sine 30, because that's what we calculated up here. And minus the frictional force, which is the 13 newtons, which is 12.7, just to 3 significant figures. We'll get it back to 2 at the end of this part of the question. So this is equal to 24.5 minus 12.7, which gives us 11.8, which is equal to 12 newtons down the slope. So that's equal to that ma there. Now part E says calculate the acceleration of the block. So just using Newton's second law, we know that ma is equal to this net force. So 5.0 times the acceleration is equal to the 11.8. And so this tells us that the acceleration is equal to 11.8 on 5, which is equal to 2.36 or 2.4 meters per second to two significant figures, and acceleration's a vector, so we better give a direction down the slope. And finally part F, calculate the speed of the block at the bottom of the slope if it starts from rest at the top of the slope. Now there's two ways to do this. We could either consider energy. We could assume that all the gravitational potential energy at the top got converted into kinetic energy at the bottom. Or as we've already got the acceleration and we know that the initial velocity is equal to 0 and the distance it's gone, we can use the kinematic equations. So let's do this using the kinematic equations. We can use the kinematic equation v squared is equal to v naught squared plus 2 times a times the displacement. Substituting in, we get 0 squared plus 2 times 2.4, we'll put it as 2.36, keep more significant figures for now, times the distance down the slope, which is 2.0. Solving that, we get 9.44. And then v is equal to the square root of 9.44. Solving that on the calculator, we get 3.07, which is equal to 3.1 meters per second down the slope, and that's to two significant figures. Problem 4. A driver in a car of mass 1,500 kilograms, and this mass includes the mass of the car and the driver, is travelling at 80 kilometers per hour. So V naught is equal to 80 kilometers per hour. Let's just convert this into meters per second. So 80 times 1,000 over 60 times 60. Solving that one on the calculator, we get 22.22 meters per second. When he sees a dog step onto the road in front of him, he slams on the brakes. If the coefficient of static friction between the car and the road is 0.9, so mu s is equal to 0.90, and we're told we can assume the wheels on the car continue to roll. If the wheels on the car skidded on the road, then we need to know mu k rather than mu s, and we're now asked to calculate A, the maximum acceleration of the car as it stops. So the acceleration of the car as it stops comes about due to the frictional force. So the frictional force is equal to the normal force times mu s, and the normal force of the car on the road, as long as the road's relatively flat, is just due to the normal reaction force, which is equal to the weight of the car. So the normal force in this case is equal to the weight force, so it's mg mu s, and substituting in, we've got 1,500 times 9.8 times 0.90, and solving that one on the calculator, we get 13,230 newtons. And so that's the frictional force, and now we can calculate the acceleration of the car. And so we've got ma, which is ma is equal to the frictional force, and so 1,500 times the acceleration is equal to 13,230, and so the acceleration is 13,230 over 1,500. Solving that on the calculator, we end up with 8.82 meters per second, which we should just give to two significant figures, so 8.8 meters per second, and this is a deceleration. It's slowing the car down. Now part B of the question says the stopping distance of the car. Okay, so we now know what force is acting to stop the car, and we need to work out the distance it travels over that time. So we can do this with the kinematic equation. We can use v squared is equal to v naught squared plus 2ax where x is the distance travelled. So we know that the final speed of the car is 0 because it comes to a rest. That's what the stopping distance is, how long it travels before it comes to rest. So v naught squared, this is the initial velocity squared. So it starts at 22.22, and we should square that, plus 2. Now, the acceleration is acting in the opposite direction to the velocity because it's acting to slow it down. So that's got a negative sign in front of it, times x, and this x is the stopping distance. And so we can move this part here over to the right hand side and then divide by the 2 times 8.82, and we have x is equal to 22.22 squared over 2 times 8.82, and solving that one on the calculator, we end up with 27.9, which is equal to 28 meters to 2 significant figures. And then finally part C, the net force felt by the 80 kilogram driver as the car stops. So the net force, F is equal to ma, is just the mass of the driver times the acceleration, and so this is just equal to the 80 times 8.82, which is equal to 705, which is equal to 710 to 2 significant figures, newtons 2 sig fig, in direction opposite to original motion, as this force is acting to slow the driver down. Problem 5. So in this problem we're looking at a collision between two bores. Initially we've got two bores heading towards each other, both with a velocity v initial. This is mass 1 and this is mass 2. And then after the collision we've got two bores heading away from each other, one with velocity vf1, which stands for v final 1, and one with velocity v final 2, and this one's m2 and this one's m1. And we're told the diagram shows a collision between two bores. You can see how the bores are moving before and after the collision. If m1 equals m2 equals 0.50 kilograms, okay, so now we've got m1 equals m2 equals 0.50 kilograms, and the initial velocity is equal to 2.5 meters per second. We need to start by calculating the initial momentum of the system. Okay, so the initial momentum is equal to m1 v initial 1 plus, sorry, that should be a 1, plus m2 v initial 2. And so remember, these are vectors, so they do have a direction. So we've got m1, which is 0.50 times 2.5, plus m2, which is 0.50 times this, but this is in the opposite direction. The initial velocity here is in the opposite direction to this one, so we can take the left to the right as positive and to the left as negative, so this is minus 2.5. You can see these cancel each other out and we get 0. Now part B says calculate the initial kinetic energy of the system. So initial kinetic energy is equal to a half m1 v initial 1 squared plus a half m2 v initial 2 squared. Now kinetic energy is not a vector, so the direction of this velocity doesn't matter. So we've got a half times 0.50 times 2.5 squared plus a half times 0.50 times 2.5 squared, and solving that one on the calculator we get 3.1 joules. Now part C of the question says if Vf1 is equal to 2.0 meters per second, then we need to calculate Vf2. So Vf2 is what we're trying to find. Now to do this, we're going to need to use the law of conservation of momentum. So we know that the momentum up here was 0, So we need to have zero momentum down here as well so that the momentum is conserved during this collision. So we know final momentum is equal to 0, and it's equal to m1 vf1 plus m2 vf2. So this is equal to 0.5. Now we're taking to the left as negative. So this is minus 2.0 plus m2, which is 0.5 times vf2, and that is equal to 0. And so moving this over to this side, we've got 1.0 is equal to 0.5 times vf2. And so vf2 is equal to 1.0 over 0.5, which is equal to 2.0 meters per second. And that, because it's positive, is to the right. And then part D says, is the kinetic energy conserved in this collision? Well, to answer that, we'll need to work out what the kinetic energy final is. So it's a half m1 v final 1 squared plus a half m2 v final 2 squared. And so that's a half times 0.5 times 2 squared plus a half times 0.5 times 2 squared. And so that is equal to 2 joules. And so it started with 3.1 joules, it ends up with 2 joules, so this tells us that kinetic energy is not conserved. Now let's clear some space to do the next half of this question. And so in the second half of this question we have the same diagrams, but we've got different values. We're told that m2 is equal to 2m1 and m1 is 0.300 kilograms. So m2 is equal to 0.600 kilograms, m1 is equal to 0.300 kilograms, and the initial velocity is equal to 2.2 meters per second. And so part E asks us to calculate the initial momentum of the system. So the initial momentum is equal to m1 v1 initial plus m2 v2 initial, and so this is equal to 0.300 times 2.2 because it's going to the right, so this is positive, plus 0.600 times minus 2.2 going to the left, so this one's negative. So solving that one on the calculator, we end up with minus 0.66 kilogram meters per second. Or you could put it as Newton seconds if you want, and the negative indicates that it's going to the left. Part F asks us if Vf1 is equal to 1.2 meters per second, calculate Vf2. So here we use conservation of momentum. Which tells us that the final momentum is equal to the initial momentum, which is equal to minus 0.66. So the final momentum is m1 vf1 plus m2 vf2, and that's equal to minus 0.66. So we've got 0.300 times 1.2. And this is in the negative direction, so we should put a negative in front of that one there. Plus 0.600 times Vf2 is equal to minus 0.66. So moving this one over to this side, we've got 0.600 Vf2 is equal to minus 0.300. And so Vf2 is equal to minus 0.5 meters per second, which is 0.5 meters per second to the left because of that negative sign. And now part G asks us what's the initial kinetic energy. So that is equal to a half m1 v initial 1 squared plus a half m2 v initial 2 squared. So that's a half times 0.300 times 2.2 squared plus a half times 0.600 times 2.2 squared. And solving that one on the calculator, we end up with 2.178, which is 2.2 joules to two significant figures. And then finally, part H asks us, is the collision elastic, inelastic, or perfectly inelastic? So we need to work out the final kinetic energy in order to know this. The final kinetic energy is a half times m1, which is 0.300 times v1 squared, so minus 1.2 squared, plus a half times 0.6 times 0.5 squared. This is equal to 0.291. So it's lost kinetic energy, which tells us that it's an inelastic collision. In order to be perfectly inelastic, they would need to stick together, and they don't stick together. So we can see this isn't actually going in this direction, it's going in this direction after this second collision. Problem 6. So in this problem, we've got two cars heading towards each other. We've got one car here with a mass of 1,100 kilograms. It's heading with a speed of 60 kilometers per hour. So let's just work out what its initial speed is in meters per second. So let's call this one car 1. So we've got V1 initial is equal to 60 kilometers per hour times 1,000. So that'll be meters per hour divided by the 60 times 60 to get it into meters per second. And this gives us 16.667 meters per second. And then we've got a second car, which is heading in a different direction. It's got a mass of 1,500 kilograms and it is traveling with an initial speed of 45 kilometers per hour. So let's just work out what that is in meters per second. V2 initial is 45 times 1,000 over 60 times 60, which gives us 12.5 meters per second. Now in the first part of this question, part A, we're told that car 1 is initially travelling northwards and car 2 is travelling in the southerly direction. And we're asked to calculate the momentum of the cars immediately after the collision. Okay, and we know that they stick together because we have a perfectly inelastic collision. So afterwards, these two cars are stuck together with a total mass of 2,600 kilograms. Okay, so for part A, we know that the final mass times the final velocity is equal to the initial mass of car 1 times the initial velocity of car 1 plus the mass of car 2 times the initial velocity of car 2. So we know this because we know that momentum is conserved. So all we need to do is substitute our numbers into this equation here. Now the velocities in this case, this one's going northwards and this one's going in the southerly direction. So these velocities are going to have opposite signs. So we've got 1,100 times 16.667 plus 1,500 times minus 12.5. So solving this one on the calculator, we get minus 416.3 Newton seconds. So we can write that as 420 Newton seconds in the southerly direction because it's in the direction that the negative one's travelling in, so south. Now in part B of the question, we're told that the initial velocity, car 1 is now travelling northwards and car 2 is travelling towards the east. So we've got car 1 like this going northwards and car 2 like this going east. And so we know that when we work out the final momentum, we have to add these as vectors, as momentum is vectors. So mass final times velocity final, the final momentum, is equal to m1v1 initial plus m2 v2 initial, and I've drawn the little squiggly line under these v's to make it very clear that they are vectors, so they have a direction. So when we add them, we have to add them vectorially, so we draw the vectors head to tail. And so this is our resultant vector here that we're trying to find. Now this is m1 v1 initial, so this is the 1100 times 16.667. So this one is equal to 18,333.3 Newton seconds, and this one is the mass 2, so that's 1,500 times velocity 2, which is the 12.5, and multiplying those two together we get 18,750 Newton seconds. And so to work out our resultant, we can just use Pythagoras' theorem, and we take the square root of 18,333.3 squared plus 18,750 squared. Solving that on the calculator, we get a magnitude of 26,224, which is equal to 26,000 Newton seconds to two significant figures. Now, this is a momentum, so it is a vector, and so we should include an angle as well. So if we can work out this angle, then we'll know that it's north, this angle east. So in order to work out this angle, we can use SOHCAHTOA. And the ones we know are the opposite and the adjacent, so we'll be using tan. So tan theta is equal to opposite, which is 18,750, over adjacent, which is 18,333.3. So solving that on the calculator, we end up with theta is equal to 46 degrees. And so our momentum is 26,000 Newton seconds north, 46 degrees east. And so this would be our final answer. Problem 7. So in this problem, we're told that a 1,200 kilogram car travelling at 80 kilometers per hour runs into a pole. It brings the car to an abrupt stop. The collision lasts 0.20 seconds. And amazingly, the pole does not bend. Part A, we're asked to calculate the impulse experienced by the car during the collision. So initially, we've got the car travelling at 80 kilometers per hour and the pole, and then after the collision, we've got a stationary car, so V final is equal to 0. So we know that the impulse is equal to the change in momentum, and it's also equal to force times time. So in this case, it's easiest to use the change in momentum. So this will be m V final minus m V initial. And the mass of the car, we're told, is 1,200. So this is 1,200 times V final, which is 0, minus V initial. So minus the 80 kilometers per hour. So 80 kilometers per hour is equal to 80 times 1,000 over 60 times 60, which is equal to 22.22 meters per second. And so this is equal to 1,200 times 22.22 with a negative sign. Solving that on the calculator, we end up with 26,667, which is equal to 27,000 Newton seconds. And that negative sign indicates that it's in direction opposite to the direction the car was initially travelling in. And then part B asks us to calculate the average force experienced by the car during the collision. So now we can use this part. So we've got the impulse, which is the change in momentum now, and now we can work out the force. So the force is equal to the impulse over the time. So that is equal to 26,667 over 0.20. And so solving this, we get 130,000 newtons, and then it's going to have the same direction as the impulse, so in direction opposite to direction car was travelling. Problem 8. In this problem, you're given the force time graph, such as this one here, and asked to use it to calculate the force experienced by a 2 kilogram mass. Now, in part A of the question, it says to calculate the total impulse experienced by the object in the time interval shown. So in order to calculate the total impulse, if we have a force time graph, we need to work out the area under the force time graph. So in order to do that, let's split this up into 3 sections. So let's start by doing this triangle section here. So let's call this 1, and then we'll do this rectangular section here, and then we'll do this second triangle here. And the force here is equal to 2 newtons. So to work out the area of this triangle, we need to use half the base times the height. So area of section 1 is equal to a half. Now the base, we're going from 1 to 2. So this length here is 2 minus 1, which is 1. And the height, it goes up to 2 newtons, so that's times 2. So this is equal to 1 newton second. Now the area of section 2, this is a rectangle. So the area of a rectangle is just the base times the height. So the base, we're going from 2 to 4. So this has a length 4 minus 2, which is 2, times the height, which is again 2. So that is equal to 4 newton seconds. And then finally, this last triangle, we need to do half the base times the height again. And so the base, we're going from 4 to 6. So 6 minus 4 is 2, so the base has length 2, and the height is again 2. So this is equal to 2 newton seconds. So to get the total area, we just have to add these up. 1 plus 4 plus 2 gives us 7 newton seconds. So 7 newton seconds is the total impulse felt over this time interval. Part B, calculate the acceleration of the object at t is equal to 3 seconds. So at 3 seconds here, we're told that the force acting on the object is 2 newtons. So F is equal to 2 newtons, and we know that F is equal to ma. So A is equal to F on m, which is 2 newtons over the mass, which was 2 kilograms, and so that is equal to 1 meter per second is the acceleration. And the direction will be in whichever direction that force is acting. Part C says if the object has an initial velocity, so v0 is equal to 2.0 meters per second, northwards, and the force always acts in the northerly direction, calculate the velocity of the object at the end of the time interval shown. So we've got the total impulse, and we know that impulse is equal to the change in the momentum, which is equal to m times the final velocity minus the initial velocity. And so we've got 7.0 is equal to the mass, which is 2, times the final velocity, which we're trying to find, minus the initial velocity, which is 2.0. And so 7 divided by 2, that's 3.5, is equal to the final velocity minus the initial velocity. And so this tells us that the final velocity is equal to 3.5 plus 2, which is 5.5 meters per second northwards. Problem 9. So in this problem, we have a 1 kilogram mass. And we're told that it travels around a circular path with a radius of 1.2 meters. And the period of the motion is 0.20 seconds. So part A says calculate the circumference of the circular path. So the circumference of a circle is just equal to 2 pi r. So this is 2 times pi times 1.2, and just solving that one on the calculator, we end up with 7.5 meters to two significant figures. Now part B asks us to what is the speed of the object. So in order to do this, we can just use the formula speed is equal to distance over time. So we know it covers one circumference, one complete cycle, one complete circle in 0.20 seconds. So the distance is the 7.5 meters and the time is the 0.20. And so solving this on the calculator, we should just keep the extra significant figure from here, just to solve it here, and we get 38 meters per second is the speed of the object going around the circle. Now in part C, we warn this is a bit tricky, averaged over one period, what is the average velocity of the object? Well, look at this point on the circle, it's got a velocity in this direction, a tangent to that circle. At this point, it has exactly the same speed, but it's traveling in an exactly opposite direction. So what actually happens is that as we average it over one complete circle, all these speeds cancel each other out because for each point there's a speed in exactly the opposite direction. And so the average velocity is actually 0. Now the other way to think about this is that if it starts here, goes one complete circle and gets back here, well, what's its displacement? It's back to where it started from, so its displacement equals 0, and the average velocity is equal to the displacement over the time, and the displacement is 0, so this is 0. So that's two ways to solve this one. Part D, we're asked what is the acceleration of the object at the point shown. So to do this, we can just use our circular motion equation. A is equal to the speed squared over the radius. So this is 7.54 squared over 1.2, and solving that one on the calculator, we get 1,184, which to two significant figures is 1,200 meters per second. And then as it's an acceleration, we should give a direction. The direction for the acceleration is towards the center of the circle. And then part E, we're asked what is the net force acts on the object at this point. So we just know that the net force is equal to the mass times the acceleration. So this is just 1.00 times 1184. So this is equal to 1,200 newtons towards the center of the circle. Now, problem 10. In this problem, we're told that a car follows a road with a radius of curvature of 30 meters. So it's going around some curved road like this, and this has a radius equal to 30 meters. The car has a mass of 1,200 kilograms and is traveling with a speed of 45 kilometers per hour, which is equal to 45 times 1,000 over 60 times 60, which is equal to 12.5 meters per second. Now in part A of the question, we're asked what is the magnitude of the acceleration of the car. So we know that the acceleration is equal to v squared on r, and so this is equal to 12.5 squared over 30, and solving this one on the calculator, we get 5.2 meters per second. Part B says what net force is acting on the car as it follows the curved path. Well, the net force is what is causing this acceleration. So we just have F is equal to ma, so that's 1,200 times the 5.2, and solving that on the calculator, we end up with 6,250 newtons. So we can either round this up or round it down. Let's round it up to 6,300 newtons. And part C, This net force is provided by the frictional force between the tyres and the road. What minimal coefficient of static friction is required between the tyres and the road in order to make the car follow this path? So we have the net force, and we know that that is equal to the frictional force, which is mu s times the normal force. So this is equal to mu s times mg, and so now substituting in our numbers, we've got 6,300 is equal to mu s times 1,200 times 9.8, and so mu s is equal to 6,300 over 1,200 times 9.8, and solving this on the calculator, we end up with 0.53. So the coefficient of static friction needs to be at least this in order to keep the car on the road in this case. If it got less than this, then the car would start to swerve off